record and share this. So let's just chat about a problem that I kind of generated a little bit ago. So I have this polynomial, and so I'm going to use this as a way to talk about a couple of pieces. This is really intended to be largely review, but also something that's going to kind of help me launch into something. So this is a big, obnoxious polynomial, right? That looks kind of scary, doesn't it? So what I wanted to do is just use that as a format to just discuss a couple of concepts. Number one, from the previous unit, you tell me something. The limit as x goes to infinity of f of x. We spent several days talking about the end behavior of this particular function and others. What is the only piece of data you care about in that story? There's one number that matters to answer that question. What is it? 10. And since that number was positive, guys, what do you know? The end behavior is going to go which way? Up to positive infinity. That's something we know, right? So if my goal was to graph it or find the roots, or I know it's going to go up to the right. What's going to happen to the left as I go to negative infinity? There's something else I need to look at now. Not only do I need the 10, what else do I need to know? I need to know the power, right? What was the power on this thing? The fifth. Now, I did something for you. Did you notice that the way I wrote this polynomial, how did I choose to write it? What do we call this form? Standard. And that makes it nicer because, in fact, you know, if you're going to actually name the lineup of a team, let's say you're going to discuss, let's say the people that play for the Kansas City Chiefs. Who's the first person you're going to mention when you talk about the Kansas City Chiefs? There's one person, there's one name, undeniable, that everybody goes, yeah. Who is it? Patrick Mahomes. Why would you say Patrick Mahomes is being significant? Because basically, without Patrick Mahomes, were they winning a championship? Not a chance. The dude is amazing, right? See, you're going to go with that power player, the person that is the most significant, right? In a company, you might name the CEO because they're the person that's kind of making the rules. This guy right here is Patrick Mahomes. I'm a 49ers fan. Patrick Mahomes kind of makes me sad. But, you know, anyway, I get it, though. Have been my whole life, so there's no bandwagon effect. It's just sadness right now. Did you guys hear that Jimmy G's out now? They were doing so good, but then you lose Bosa and Jimmy. Oh, this just sucks. Anyway, so we learned this, right? Now, we added a little bit of a rule yesterday. So let's talk about the possible rationals. So we're going to see something. I have a set of notes that I'm going to have you guys look at today that kind of organizes this, but I wanted to make sure that everybody got what I was shipping at you yesterday. So where do we start this journey? When we look for one of those possible rational roots. I should actually put roots here, but sometimes we just say rationals. But where do we go first? This was from yesterday. We go to we look at the 32. Can you guys tell me what numbers nicely divide into the number 32? Start easy. Go 1. What would be next? 2. How about 3? No. How about 4? Yeah. How about 5? No. 6? No. 7? 8? Yeah. 9, 10, 11, 12, 13, 14, 15, 16, and 32, right? Hey, just so happens 32, that was kind of a nice one. It was just powers of 2, so that was pretty easy. And then not only do we look at that, we also look over here not only at a sub 0, that's what you were kind of fishing for, is a sub 0, you also look at a sub n. That's a 10, right? So what are the magic numbers that go into that guy right there? 1, 2, 5, 10, right? 1, 2, 5, 10. Okay, So when we looked at the possible things to start with, we started with literally an infinite number of possibilities. And now, sorry, this kind of sucks. I took it from an infinite number of possibilities down to 24. Did that help a little bit? Okay, so when we go through all of that, we do a bunch of stuff. So I'm just going to do one thing just to see what you guys think. Let's try the number, let's try the number 5, just for fun. Actually, yeah, I think, no, actually I'll do the number 4. Let's see if you guys remember how to do synthetic division from the last few days. See if you guys remember the process. So is 4 a legitimate possibility to be a root of this problem? 100% legitimate, it should be fine. So what's the first step of my journey to do synthetic division? Because I'm hoping what's going to pop right here. I'm hoping it's 0, and if it's 0, I took my 5th degree polynomial and I got it down to a 4th degree, which is going to make it easier, okay? So first step, drop our 10. Now what happens? We multiply 4 by 10, we get 40, and that gives me negative 23. Now I'm going to start getting uncomfortable with the sides of the number, so I'm going to start using a calculator here to do some of this. I got negative 92, I got 42, I got 168, I got 159, 636, yikes. This is getting uncomfortable. Are we going to get 0, by the way? Not even close. That's awful. 2,448 plus 32 is 2,480. Ooh. Okay, so did we actually land where we wanted to land? That answer is a big fat no. We did not land where we wanted to land, but I know something. There is a coordinate on this curve right now. What is the coordinate on the curve? It's not just that 4 failed. It's that at 4, where's the function? It's at positive 2,480. So that's called the remainder theorem, is that if you do the synthetic division, whatever's sitting left over at the end of my story actually is a coordinate on the curve. So by the way, if you're thinking about that, do you think the root's going to be anywhere near the number 4? It's up at about 2,500. You think it's going to get down to 0 real quick from there? It might, but I'm kind of doubting it a little bit personally. Okay? Now, for the sake of time, I did something for us. And this is probably going to look a little bit strange to you when I first show it to you. Please go away on that thing. That's what I wanted. I wanted that to just reduce for a moment. I made a little bit of a spreadsheet right here. And let's do a new share to the people that are online. And I'm specifically going to take you to the line we just talked about, the number 4. Let's see if we can find it. See the line 4? Is that exactly the same line that we had on your paper? So guys, what I did is a whole truckload of synthetic division for you. But what you're not seeing is that middle line. Remember, we multiply and then we add down to get that? These are just the answers, okay? So a new thing that I showed you yesterday, how do I unzoom out of this thing and make it a little bit smaller? Is it Control minus? Control Shift minus? What's the trick? Because neither of those worked. Well, I know I could go here. Maybe like that. Maybe that'd work. Okay, so I gave you a little bit of a trick. I'm going to go ahead and scooch over a little bit right here. I guess I need to go to 75. Hopefully that's not so small that you guys can't see. But I gave you a little trick that they figured out. Let's talk about upper and lower bounds. That was another thing that I discussed with you guys yesterday. Okay? So when there was an upper bound, do you guys remember what happened? all of the answers were what? Positive. So can you guys look at this list? Can you find where the answers became all positive for the first time? Remember, these right here are the values that were the actual numbers, if you will. So these aren't the coefficients. These are the things that I'm dividing by. What number made them go all positive? 7 did, which means if I am searching, what about all of this junk right here? Can I just delete it? Completely irrelevant information. I'm searching for something better. Okay, let's go and see if you could find the lower bound. What did we say happened on the lower bound? They should alternate signs. So where do you see an alternation of signs? Plus, minus, plus. Let's see. Did it alternate at 4? Plus, minus, plus, minus, plus, minus. Did it alternate here? That did. Did 3 alternate? I think it did. Did negative 2 alternate? How about negative 1? It did, didn't it? So wait a minute. If I saw alternation at negative 1 and I saw it all go positive at 7, what does that tell you guys? Where are all of the answers to this problem? In between negative 1 and 7. So if we go back to that crazy list, could I throw out a whole bunch of answers in that list of 24 that I listed? You follow me? So these are just kind of smart ways to play the game. Now there's one other little thing that was, I told you, is called the intermediate value theorem. Check out what happens between negative 1 and 0. What do you see happens between negative 1 and 0? Because I know at negative 1, it's sitting down at negative 160, isn't it? What is happening at 0? It's at 32. So what had to happen between negative 1 and 0? It had to cross the x-axis, didn't it? Is that kind of helpful? So I know in my list, I could look through it and I could look for some fractions that are between negative 1 and 0. I'm going to write that down. This is my lower bound. This is my upper bound. So somewhere between negative 1 and 0. Where else do you guys see a root? Is there anywhere else that you see one that goes from negative to positive? Because I kind of honestly don't. That's kind of weird, because I actually know the answer. So I'm a little bit surprised that I don't see more. But I'll just kind of jump out of this here, and let me go ahead and come back to here, and I'll tell you what I multiplied out. And let's see if this actually works. What I had was x minus 2 cubed multiplied by 2x plus 1 multiplied by 5x minus 4. That's what I actually multiplied out. So what are the roots? Again, this is going back a couple of days ago. What are the roots? 2, but what would we say about that number 2? It had multiplicity 3. It was a triple root, right? What else do we have? We have negative 1/2, whose multiplicity is 1, and we have positive 4/5, also multiplicity 1. Everybody doing okay with there? Now, let's go back and look at the list that we generated. Was the number 2 in my list up here? It was 2 over 1. Was negative 1/2 in my list up here? Negative 1/2. And the last one was 4/5. Was 4/5 in my possible list? It's actually pretty nice and significant. So you guys kind of see how all this stuff plays out? Now, if we could find one root, our life would get a lot better than where it is right now. And what's a little surprising is I didn't actually notice something. There's a root specifically supposed to be at the number 2, isn't there? I don't remember seeing it hit 0 anywhere, but I don't know if I messed something up in my work, but that's what happened. So the last new thing that I wanted to give you today, this is kind of important, is, sorry, Descartes comes up again. Descartes is a crazy dude. This is called Descartes' rule of signs. And you need this one. But just like the greatest lower bound and the lowest upper bound, I almost have to close my eyes and say that because it's weird to say the greatest lower and the lowest upper. Doesn't that feel like you're saying it wrong? I want to narrow it in. So we found out that these numbers were between -1 and 7, right? I wanted this lower bound to be as big as possible, and I wanted this upper bound to be as low as possible to squeeze it in. I don't want to search. Do you guys like a long problem that takes you 45 minutes to solve one? I don't think so. So we want to squeeze it in. Well, Descartes did one more thing, and this is super bizarre. Honestly, I don't know how the guy came up with some of what he came up with. But it's called the rule of signs. So check this thing out. The problem started positive, didn't it? Let's find out how many sign changes there are. It changed here once. It changed here twice. Changed again 3 times. Stayed the same and then changed back. That was 4 sign changes. You guys with me on that one? Now again, to write this out thoroughly is super duper hard to do, but what Descartes figured out is for the positive roots, all you have to do is count the number of sign changes. And how many did we just get? We got 4 of them. Now, you got to be a little bit careful here because when Descartes' thing, that was not about rational numbers. That was about all answers. So he said, hey, if you're looking for the positive roots, there could be as many as 4 of them. Or 2 or 0. And what he figured out is if you do the sign changes, so let's go with a different number. What if you had seen 3 sign changes? Descartes would have said there's either 3 positives or 1 positive, period. So what am I always going down by? 2's. What if there had been 6 sign changes? Then it would have been a 6, 4, 2, or 0. You guys with me so far? And Descartes, again, was super duper smart. And so what he did is he made a rule for the pluses. And in reality, he didn't make a rule for the minuses because what he did is he said, well, let's look at f of negative x. So you tell me, what happens if you do f of negative x? What does f of negative x to any graph do is it flips it over. And it took all those negatives, and what did it do to them? It flipped them over and made them positive. So Descartes says, oh, sweet, let's just take a look at f of negative x. Now, this is my notation. I could be more thorough. I don't want to be because it takes time. But you guys tell me, what would happen if I replace x with negative x right here? Wouldn't I get negative x to the 5th times 10, and what sign would I have? Would it be a positive or a negative if I took a negative x, raise it to the 5th, and then multiplied it by 10? A negative. Now, the fact that it's negative 10x to the 5th, I could care less. I just care. Descartes' rule of signs just says, what sign do you have? So, guys, what would happen if I replace x with negative x here? And I raised it to the 4th power. It's positive. Times a negative 63, it stayed negative, didn't it? I don't care that it's 63. I just care that it's negative. What about here? If you replace x with negative x, raise it to the 3rd power, and then multiply it, it's still negative. And then I come over here. This is sweet. I didn't actually plan this. Take negative x, square it, and then multiply it by negative 9. What happened? It's negative again. And then negative 24 times negative, oh, that's a positive. And then it stayed positive. This is my favorite example I've ever made. How many sign changes do you see? 1. So Descartes was like, oh, there's 1 negative. That's my favorite thing to happen in a problem, because if I'm searching and I found 1 negative, what would that tell you? Stop looking. There aren't any more. What does this guarantee? It guarantees 1 negative and only 1 negative. So as soon as you find that one, you're done. Isn't that kind of nice? Now, my favorite problem that you'll see occasionally is somebody will hand you a problem like this. X to the 4th plus x squared plus 2. See that? How many sign changes do you see? None. So don't even bother to look at the positives. Follow me? See how fast that was? So if I made my big list and I talked about all the ideas, maybe I make it like 28 or something like that. There's no sign changes, so don't look. Let's look at f of negative x. That would be positive x to the fourth, positive x to the 20th. Hey, what does that mean? Hey, there's no positive roots and there's no negative roots. What does that mean? There are no roots. Quit looking. Did that save us some time? Descartes' rule of signs is a super slick little sucker that will tell you whether you want to look for things or not. So, how many real roots could this thing have had? It could have had 4 and 1 for 5. It could have had 2 and 1 or 3, or it could have just had 1. In reality, what we have is we had 3, 4, 5. So how many positive roots were there in this problem? Exactly. Look at it. 1, 2, 3, 4. Did that match? How many negative roots were there? And that's what Descartes' rule of signs guarantees. Okay, so that was my one add-on for today, was Descartes' rule of signs. Is that a hard rule? What do? What's the rule? You count the sign changes, and if there was 3 sign changes, what would you say? You'd say 3 or 1. What if there was 2 sign changes? 2 or 0. That only tells you about the positive roots. And then if you replace x with negative x, you can use the same rule. So in the back of the room, there's a note card that I'd like you to snag. We're going to kind of go through this together. This is going to mimic what you're going to do. Go grab one off the back counter for me. I'll give you a chance to stand up and stretch your legs for a moment. And we're going to get a good chunk of time for you guys to actually work independently or in your teams today. All right. Okay, so let's see what happens here. So what are my possible rationals, everybody? So let's see if we can make the list. We put a plus or minus out front. Can you make your list, everybody? Because I was actually thinking about making a quiz today, and I just wasn't sure if I wanted to do this. I probably should have had you grab a graphing calculator while you're at it, too. If you don't have one, you might want to snag one. It's hot. Okay, so Abby, what possible numerators exist in this story? Whoa, wait, hold on. In this one right here? Sweet. Brianna, what are the possible denominators in that thing? Sweet. Okay, so D, is it in the realm of possibility that 5/3 could be a root? Is that up here? It is. Devin, could 5/2 be a root? Is that in my list? 100%. How about -4/3, Montserrat? Is -4/3 in my realm that it might be a root? No. Okay. So we have a list of them. And some teachers actually make you make a formal list where you can't write it as a complex fraction like this. Could we do that? Could we write all these over 1 and then all of these over 2 and then all these over 3? I'm a little lazy though. I don't really want to do that. Do you guys appreciate that? I'm letting you be a little bit informal here. Okay, so now let's talk Descartes. So we've got this list and we've narrowed down the infinity down to 4 by 1, 2, 3, 4, 5, 6, to 24 options. Actually 48, sorry, plus or minus. There's 48 possibilities. Do you guys want to check all 48? That's a hard pass. Okay, so let's talk about what we know easy. How many positive roots are there? What did Descartes figure out? How many sign changes do you see? I saw 1. That, by the way, is my favorite thing because then it's 1 or, well, I guess 1. Descartes says you have to go down by 2s every single time. Now, Descartes was a smart cookie, I get that, but this isn't that big of a deal. Because I showed you something the other day. If 1 plus root 2 is a root, what is also a root? 1 minus root 2. So every single time you do these things, you always get them coming in these little pairs. So the reason he goes down by 2s is because when you solve that on the quadratic, you get that plus or minus. They always come in these little partnerships. So, favorite thing, if you ever found 1 positive root, what do you guys know? Then the rest of them have to be negative. So the question is, how many could be negative? Now, it depends on you how you want to do this. Some people like to be more formal. Some people like to be less formal. I personally choose to be less formal. What would happen if I replaced x with a negative, I raised it to the 4th and multiplied it by 12? Would I get a positive or a negative answer? Positive. What about if I took a negative, raised it to the 3rd, and then multiplied it by 4? Negative. I took a negative, I squared it, and then multiplied it by a negative. A negative times a negative is a positive. Well, shoot. You guys understand my plus and minus chart? Because the only thing I'm going to use this for is a count. So how many sign changes do you see? Every year I have some people count this wrong. How many sign changes are there? Everybody hold up your fingers. I'm seeing 2, and I'm seeing 2, and I'm seeing 3. So we have some debate. Where did the problem start? So it changed definitively here. Did it change here? No. Did it change here? And it changed here. So did it change? How many times? That's 3, ladies and gentlemen. So do not just write 3, because Descartes' rule is a little more complicated than that. It was 3 or what? Or 1. So you tell me, how many roots could this thing have? Now, from last week, a 4th degree could have as few as how many roots? A 4th could have as few as none at all. It could have as many as 4. What can this one actually have? It either has 4 of them or it has 2 of them. So does it actually have to cross the x-axis then? At least twice, right? The question is it going to be 2 or is it going to be 4? So can you guys find g of negative 2? Now, I know that when you go back in time, what does that tell you to do? If you say g of negative 2, wouldn't that tell you to go plug it in, raise it to the 4th, multiply it by 12? I hate doing that. Does that take a long time? So I don't do it. I go this way. I'm like, fine. I have this theorem that says plugging it in is the same thing as synthetically dividing it. Would this be faster to synthetically divide by negative 2 instead of raising 2 to the 4th power and then the 3rd power and the 2nd power? Is this faster? It's equivalent though, isn't it? You guys like that as a trick? Instead of plugging it in, ironically, you divide it and you get the same answer. That's so counterintuitive. So I got this. That's negative 20, 40, negative 23. I love the fact that you can write it almost as fast as you can think. Okay. What does that tell you guys? The fact that I got that number, what did that tell me? It's a root. And in fact, now I have this thing that was a fourth degree. What does this represent now is 12x to the third, isn't it? Minus 20x to the second all the way down. Hey, guess what? That number is now. It's a 5. What numbers go into 5? Isn't it just 5 is 1 and 5? Look at my list of possible things to look at. What's gone now? What can't be a root anymore? 2 can't be a root. What else can't be a root? 10 can't be a root because they don't really exist. See, you could kind of go like that and say, well, those are not even on the table anymore. I can't have it. So every root that is left has to be a 1 over something or a 5 over something. That's all that remains. And so, did you guys plug all that stuff in yet? You may not have had the time. Let's just double check. 12x to the fourth plus, missed that, that's a plus 4x to the third, minus 63x squared. I got all this stuff. Now, this is my way of sanctioning you guys being a little bit lazy, okay? So what would be a smart window? What do you guys think would be a smart window? Again, I'm thinking about a test coming up and you're like, I want to know what to do, but I want it to be understandable. How far left and right should I maybe start? What would be reasonable? Because by the way, we just figured something out. 10 can't be a root, didn't we? So the biggest root in my list was 5. So I think negative 5 to 5 on x should be okay. Do you think the number 10 and negative 10 is enough room on the y-axis to go? You remember how big these problems are. Is negative 10 to 10 going to be smart? Not at all. Let's go, how much? How big should we go? 50? Sure. Let's try negative 50 to 50. That's what I heard. I would probably go bigger than that, but I'm all right with it because you know what all I care about? I want to see where this thing crosses the x-axis. So, do you see anything? Let's see what you notice. We already saw that there was a root at negative 2. Does this confirm that? What kind of root do you see? Is that a single root, a double root, or a triple? What do you think? That looks like a single, doesn't it? See right there? What do you think you're looking at right there? I think I'm looking at negative 1/2, and what does it look like? It kind of looks like a double, doesn't it? And then what's this one right here that's between 2 and 3? What is a fraction? So it looks like I saw one at negative 2. It looks like I probably saw one at negative 1/2, but it was probably like a double root, wasn't it? Kind of looks like that. And then this one somewhere between, what number is between 2 and 3 in my list? What is the only fraction between 2 and 3 in this list of possibilities? Is 5/3 in there? Now 5/3 is 1.6. It looks like 5/2 is literally the only one it can be. So we're going to rewrite this thing in factored form. In fact, the polynomial you're looking at, g of x, was in fact x plus 2. It was in fact 2x plus 1 squared. And it was in fact, how do you get 5/2? I don't want to take this trivially because I get people doing this backwards every year. What factor produces the root 5/2? 2x minus 5. Now, I think we've already dealt with upper bound. What makes an upper bound, everybody? Upper bound was all positive, so can you find the upper bound in here?
What do you call these numbers? Like when they're all positive, what do you call these numbers?
You mean these remainders?
Remainders?
These are the remainders. I'm just giving you the chart of all the remainders. I just took off all the work. What number makes them go all positives, or at least all the same sign? 3 does. And so is 4 also good? 3 and 4 are good. Which one do we like better? 3. Why? Because it's smaller, right? That's the lowest upper bound. So when you see LUB, that means upper bound, but I want the upper to be small. I want the smallest roof I can be. How about the greatest lower bound? What are you looking for on lower bound? I need alternating. Now, by the way, that chart that I showed you earlier today was evidence of why I sometimes give you these, because the charts can be obnoxiously big, right? So quite frequently, one of them is the lower bound or the upper bound because the charts just get obnoxious and I don't want to take 3 pages to give you this massive chart. So that's all good. So does this fit with what we just found? Are all of the roots between 3 and -3? Look at it. Are all of these roots between 3 and -3? Let's do Descartes' rule of signs. He said there was one positive. Did we have, in fact, one positive? Five halves. He said you either have 3 negatives or 1 negative. Did we get that as well? We did. It kind of just matches through the whole thing. So I'm going to give you guys a moment. I want you to try to go through number 2. We'll talk about that in a few moments. Again, I gave you a chart so you can utilize that chart to help us find out some things. And I don't know that we're going to go through all of these pieces. I think we're just going to do number 2 and call it a day. Because I'd like you to get down and actually do some work today. Dakota, can you give me the numerators?
1, 2.
I think you may have switched them.
Oh, yeah. Okay. 1, 2, 7, 4.
Love it. Denominators? Okay, that was a little nicer list, wasn't it? So we got numbers like 7 halves, 3 halves, 21, -21. Not too long of a root. How many sign changes, Nico, are there in the original? 1. So what does that mean? 1 or 1? I guess it's just 1. There's 1 positive, so let's go find it. That's good. I like that. How many sign changes on the negative side? I see 3. Very, very coincidentally on that one, 3 or 1. Okay. I hope I gave you enough time to think through a little bit of this, and probably not enough to finish, but I want to make sure you have time to work today too. Okay, now, here's where I did something mean to you. I gave you an incomplete chart on purpose. So I used some whiteout to kind of add to it. Because do you know what the upper bound is? This is a little frustrating to me, but let's see. Where is the upper bound? What is it? 1. Right here. Because one of the little tricks that I told you is you could count 0 as a wild card, didn't I? So is that true? By the way, not only was 1 a root, but it was also the highest root that you could get. So this is the lowest upper bound. That's a 1. But guess what you don't have in your chart? I don't have the greatest lower bound, because what never happened in my ding-dang chart? And it's because this 17 was kind of big. Notice I wanted a negative here. So can you guys help me come up with a number that at least would make this thing go negative? What number, when I multiply it by 2, would do that? I think I heard it. -9? Would that do it? Yeah, let's try that. What is -2 times 9? -18. Plus 17 is -1. Did it alternate like you wanted? Okay. What is -9 times -1? 9 plus 19 is 28. See, I'm doing synthetic division. I'm just not writing that number in the middle. We're just kind of storing it up in our nugget. Oh, man. -9 times, shoot, -9 times 28. That's huge. That's -252 minus 17. Hey, does it look like it's alternating pretty good to you? I think so. I'm going to multiply that by -9. And then I'm going to add that to -21. I got 2,400. What do you guys think? Did that work? Would it have worked if you tried -8? Honestly, would it have worked? No, because -8 times 2 would be -16. I would have still had a positive. You picked the first one, and that's really the smart thing. It wasn't that hard to do. You had to make it start alternating, and you did. So good news, bad news is I know all the answers are somewhere between 1 and -9. Ew. But I do know how many positive roots are there. 1. And look what happened down here. See how 1 was a root? So what do you know? It is the only one. I handed you the only positive root. You just need to find the negatives. Now, it says, let's show that -3/2 is a root. So we're going to be done here pretty quick here. Let's go ahead and follow through this thing, and then I'm going to give you some work, because what I want to do is I want to get this thing down to the point where I have it nice and factored. So -3/2 times 2 is -3. Add down, I get 14. This -3/2 of 14 is -21. I add down, I get -2. If I multiply that, I get +3, which gives me 14 again, which gives me ooh, I made a mistake. Because -3/2, that's 2. That's -3, that's 14. That's -21. That's, where did I do that?
-17 plus 3.
Oh, is it right here? Oh, thank you so much. I'm like, no, it's not giving me 0, and it had to be. And that was 21, so it was 0. Woo, thank you, appreciate that. Okay, now, here's the cool thing. We already know that 2x plus 3 is a factor, don't we? Why do we know that? Oh, that means this is the wrong set of numbers, because our rule yesterday said synthetic division, you can't have leading coefficients. So we're supposed to cut all those suckers down a little bit, aren't we? Can you guys tell me one more root? What's another root I haven't used? I know that 2/3, that 3/2 works because I kind of gave you a hint. Did I also tell you that 1 works? Oh, let's do that. Let's divide it by 1. That's 1. That's 1, 8. That's 8. That is, did I screw that up? 1, 7. Oh, because I didn't divide this one, did I? I forgot to divide that one by 2. Did it work? Now here's the cool thing. This stands for the following. So one of the themes that I wanted to make sure that you guys heard before I stopped on this whole unit is you have to work hard for a while. But once you get it down to a quadratic, do you guys already know how to factor quadratics? So please understand, if you ever get it down to 3 pieces, can you guys factor that? Good night. What is x squared plus 8x plus 7? 2 numbers whose product is 7 that adds to 8. How about 7 and 1, right? Oh, that's x plus 7. I ran out of room, so I'm going to put the x plus 1 in front. This is my magic polynomial that honestly I can tell you I went into Symbol Lab and I typed that in and I said, hey, Symbol Lab, can you multiply that thing out so it does what I want? Does this match Descartes? How many negative roots do you see? 1, 2, 3. How many positive roots do you see? 1. Do you see all of these same numbers sitting in the list that you generated up top? We had a list that had -1 in it, did we? -3/2, is it up there? Is +1 up there? And is -7 up there? So that's kind of our journey. That's kind of where we're going to stop today. And I'm going to have you guys do a little bit of work on something just to practice some of those skills. It's not super long. It's about the same length as the notes. Okay? And it's going to be called 2.4C because I normally have 3 assignments on Chapter 2, Section 4. Not this year because we have less time. So A and B were kind of one assignment, so it's going to feel awkward that I'm calling it C. So anyway, that's going to be the end of my